Okay, so thank you all for coming and for the good turnout. So my name is Catherine Powell. I'm one of the program organisers for the 6-month program on uncertainty quantification that's taking place here at the moment, and this event is part of that program. So for those of you who don't know, each program is asked to nominate one of their program participants to receive or to be a Rothschild fellow during their stay. And the program organisers for this program were unanimous in their decision to nominate Andrew for this fellowship. So we thank the Rothschild Foundation for their financial support to support Andrew's visit and the Isaac Newton Institute as well. So the main aim of this program, many of you have participated in some of the activities so far, but those of you who haven't, the main aim of this program is to establish connections between people working in the different disciplines that contribute and make up this broad field of uncertainty quantification, in particular across applied mathematics, numerical analysis and statistics. And Andrew's work spans many of those disciplines. So it's my pleasure to introduce him. I won't speak for very long. Most of you will know him and his work, I'm sure. He's well known for his work on dynamical systems, numerical analysis in general, stochastic differential equations, Bayesian inverse problems, and also data assimilation. He's held faculty positions both in the UK and in the US, at the University of Bath, Stanford, Warwick, where he spent most of his career, and recently moved to Caltech, where he is the Bren Professor of Computing and Mathematical Sciences currently. He's supervised many PhD students and postdocs who've gone on to have successful careers in academia. All of them are here today, many of whom are very successful and prominent in the uncertainty quantification community. He's written several books spanning several disciplines, the most recent one being on data assimilation, published by Stuart. So he's been awarded several prizes and delivered many keynote talks, too numerous, I won't list them all. Relevant to uncertainty quantification, he gave a keynote talk at the SciAm UQ conference in 2014. Many of you might have been there. He served as the chair of the SciAm UQ activity group in 2015-2016, and is currently one of the editors-in-chief of the SciAm ASA journal on uncertainty quantification. So he's very active in terms of leadership in our community. So that's enough from me, and it's over to you to deliver this Rothschild lecture on the legacy of Rudolph Kalman.
Thank you, Catherine. Very nice to have this opportunity to tell you about Kalman. This is also my favourite lecture room in the whole world in which to give a lecture. Has my perfect combination of Blackboard and Beamer. This is meant to be a public presentation, and it's always difficult to know exactly what the general public means. It includes my brother in this case. But also I did intuit that it was going to be a fairly mathematical general public, and so the talk does include some equations, but also quite a lot of pictures. So it's a balance between the two. If you have a preference for either pictures or equations, there should be enough to concentrate on within either category. I'm going to talk about Rudolph von Kalman and his legacy, and in a word, or in a sentence, what he really did systematically for the first time, and in work that led to revolutions that I will tell you about, was to think about blending data with mathematical models. It's not to say that no one did it before him, and it's not to say that there haven't been important ideas separate from him, but I think that he plays a really central role in bringing together mathematical modeling and data. And I want to explain that to you by explaining what he's done, my perspective through optimization on his work, and then a personal perspective on generalizations of his methodology to many different applications. So you'll see, I think, some really nice and fairly simple mathematics, mainly quadratic optimization, and you'll see a wide range of applications. And I'll give you a little bit of historical context. Okay, so I'm going to start with some historical context. I will then tell you what Kalman himself did and describe some of the things that came out of that, and maybe the first big application other than the ones that Kalman intended that I'll talk about, is weather forecasting. And so I'll describe to you how his work has been used in weather forecasting and the impact that it's had. I'll then go on to inverse problems and explain to you how his methodology, explain what inverse problems are and how his methodology can be used in this domain, and look at a number of applications from the physical sciences, ending up with some applications in data science and the subject of machine learning and supervised learning in particular. I welcome questions, so please do question and interrupt if you'd like to. So let me give some historical context on the question of blending models and data, because of course we've always used data. The best ideas are informed by data, but the volume of data available to us now is very different to what it has been in the past. Newton was very clever. He just had one data point, an apple fell on his head, and he invented a whole theory. So there's a lot of conceptual thinking and a sparse amount of actual data. And in particular, I'd like to emphasize the fact that not only Newton's laws themselves, but things that have come out of them, like conservation laws in mathematical physics, the things that describe elasticity in fluids, they do have constants in them which are not known and which have to be learnt about from data and from experiments. But the process of the way we think about the model and the data are very separate, and the work that stems from Newtonian thinking the data and the model are conceptually different objects which come together maybe to estimate a few parameters that enter the model.
An interesting point about attributing that single data point to Newton. Surely that must have reminded him of the many thousands of times he had seen things fall.
Yeah, so there is a lot of data in that sense. It's consistent with many other observations.
Could have said to him,
and that reduces the
thinking
variance.
about all the things you've seen fall.
That reduced the variance in everything he thought. Yeah, thank you. Einstein, similar. He didn't have a vast amount of data, but he had a lot of conceptual thinking, which was combined with sparse data points. For example, the advancement of the perihelion of Mercury was something which had bothered physicists for some time, and special relativity went some way to explaining it. General relativity more or less completely explained it. But again, the data and the models were separate. Data is used to drive the questions that are asked and to fit constants that appear in the mathematical models. And this more or less is how data and models have interacted for many hundreds of years. And then over the last 50 years, and especially over the last 10 years, we've started generating data in such volumes that thinking of data and models separately is no longer necessarily the right way to think. And Kalman is arguably the first person to systematically develop a mathematical model which puts the data and the model on the same footing. So the two boards that you see here contain a generalization of what you see in the top panel here, and they will be recurrent throughout the talk. They're generalizations in that there's a nonlinear function psi on the board, which is linear in the Kalman equations here. So I'll let you absorb the equations. Let me just tell you a little bit about him. So he was born in Budapest in 1930 and lived to the age of 86, where he died in Florida 2 years ago. He studied as an undergraduate and a master's student at MIT and held positions in a number of places. University-wise, he was at Stanford, ETH, and University of Florida, where he ended his career. There's a deliberate question mark here. I mean, he has so many accolades to his name. I can't list them all here, but I've listed some important ones. I simply could not determine, maybe it's my stupidity, I couldn't determine when he was elected to the National Academy of Engineering, hence the question mark. But I did determine that it was before he was elected to the National Academy of Sciences in 2004. He won the he was awarded the US National Medal of Science. And he has prizes, the Kyoto Prize, a very broad Steele Prize from the American Mathematical Society, Draper Prize from National Academy of Engineering. His work is widely appreciated, both in engineering and in mathematics. So what did he do? Well, he wrote down a model which puts mathematical model and data on the same footing, and then asks questions about what we can deduce given that. So throughout this talk, I will be working with two equations, a dynamics model. So this describes how something evolves in time n, here discrete time, and a data model. So the dynamics model is linear and is subject to noise, which I'll call psi n. The data model is linear and subject to noise, which I'll call eta n. And the assumptions in Kalman's work were that the noises are Gaussian. And for simplicity, I've made them IID Gaussian. IID is not important, but independent is important. Okay, so he wrote down these two equations. There are continuous time analogues of this, which are more complex to describe, in a paper with Busi, which came out at the same time as the paper which I'm about to tell you about. But the key point here is that the signal, which you want to learn about, is Vn, and you know the equation it satisfies, but the equation it satisfies has noise in it, and you don't know its initial condition. So you don't know how this problem is initialized, but you make observations of this system as you go along. So this is very commonplace now because we gather data about everything. So things often evolve according to laws that we have some knowledge about that can be encoded in a predictive model, and alongside them we gather data. And then a natural question is to ask, well, what can you say about the knowledge, transferring knowledge from the data into the model? And I'll describe to you a way of looking at the Kalman filter, which is a systematic way of carrying that out, based around optimization. But let me just say a little bit more about this original paper. So the paper is from 1960 in the Journal of Basic Engineering. That doesn't sound very glamorous, does it? Most of us wouldn't choose to publish our paper in something called that, but maybe it was glamorous in 1960. Maybe it's glamorous now and I just don't know. But anyway, it's highly cited. That number is no doubt different because I wrote it a month ago. But by the standards of applied mathematics and this kind of engineering, this is an extremely high citation count. I know if you write a single paper in machine learning, you'll get this number of citations in one day, but this is a different subject area. His interest was in navigational and guidance systems, and the Apollo 11, which was the first manned operation to land on the moon, used the Kalman filter methodology as part of its guidance.
Can you remind us what year was Apollo 11?
Sorry, what?
What year was Apollo 11?
It was 1969. Yeah. So yes, under a decade to go from a paper to impact on something significant. Just a bit of notation for those of you that want to follow the detailed mathematics. I will use uppercase Y to denote the data accumulated from time 1 up to time n. And the goal of the Kalman filter is to compute the probability distribution on the signal at time n. So that's Vn that satisfies this dynamical model, given all the data accumulated up to that time. And with the assumptions that Kalman made, that is a Gaussian distribution, and therefore it's characterized by its mean and covariance. So I have to make a decision here. I know this is a public lecture, but I know that most of you are either from the two programs running in Isaac Newton Institute or from the mathematics departments here, so I'm assuming I can talk in these terms. So the mean and covariance, the center and the spread of the bell curve. And the beauty of the algorithm that goes by the name Kalman filter is that it's Markovian in structure, meaning that it's a mapping from the mean and the covariance at time n to the mean and covariance at time n plus 1. You don't have to keep the past history to be able to implement this. and this mapping only depends on the new data point, yn plus 1. All the previous data is accumulated in mn. Okay, so it's not only nice, clean mathematics, but it's algorithmically straightforward to implement. So I want to give a way of looking at this method, and I'll describe this in words in case you don't wish to take in the equations. Let me just go back to the model. What I'm about to describe is a general principle that is used throughout many mathematical models which combine data or infuse themselves with data. You use the model to make some kind of prediction as to what happens next, and then you solve some kind of optimization problem that says, I want to be faithful to the model, but I also want to be faithful to the data. So one way of looking at the Kalman filter is as a series of sequential optimization problems. You predict, which means that given the mean m at time n, you make a prediction of it by running the model forward and ignoring the noise. And that gives you a prediction mn plus 1 hat. And then you say, okay, well, I want to be close to what the model predicts, but I also want to be close to what the data predicts. So you write down an optimization problem which encodes those two concepts, being close to what the model predicts and being close to what the data predicts. And in broad terms, some version of this is what everybody is doing when they're incorporating data into models. This particular objective function is, I'll explain the notation in detail, but it's asking that you find the next point, mn plus 1, so that you're close to what the model predicts, mn plus 1 hat, and you're close to the data, yn plus 1. And there are two terms, the term that keeps you close to the model and the term that keeps you close to the data, and they're weighted. And the weighting gamma reflects what you know about the covariance of the etas that enter the data equation, and the weighting of the model, cm plus 1 hat, that's computed iteratively as part of the algorithm, and I'll come back to that in a moment. But these weightings just essentially tell you how much confidence you have in the data and how much confidence you have in the model. And you optimize and you find this compromise between data and model. So this little box here is a nice way of looking at the Kalman filter as a way of getting from the mean at time n to the mean at time n plus 1, and doing so by predicting using the model and then compromising the model with the data according to a minimization principle.
When you are minimizing, so I see there are two variables up there, capital M and capital H, which have not been, so to speak, explained or how they are used, what values are adopted.
They're assumed to be known in what I'm describing to you.
Right, so a value is adopted at the beginning of this procedure.
In this simple version. There are other things you could try and learn about them as you go along, but in what I'm doing, they're assumed to be known. So
assumed not only to be known, but you use an assumed value for them.
Yes, that's assumed no, or there will be a matrix, so they may include many values. So M describes how the model evolves, and H describes how you observe the model, and they're assumed to be known. And what you don't know is M, and you're trying to find it so that you're close to the prediction of the model, that's this term, and close to the data, that's this term. All right, there's some technical notation in here that most of you may not take in, but these norms that I use here with weights are just the Euclidean norm weighted by the square root of the inverse of the matrix that appears here. That's the covariance weighting that will be natural to any of you who study statistics. Okay, so I said this was a great algorithm, not only because it's clean mathematically, but also because it's implementable, and that's true, but it is very expensive when the state space dimension is high. So we'll come to that in the next slide. When V lives in a dimension in RD, D dimensions, this is not such a practical method because I've just described the updating of the mean, but that involves an optimization principle that involves the updated covariances, And that's expensive because they occupy order d squared storage. And when d is large, that's an issue. So this was a great idea, had an immediate impact on navigation systems and was partly involved in leading us to put men on the moon. But it does have drawbacks. And I want to describe to you, if you like, a simplification and a generalization at the same time of the Kalman filter that was motivated by the wish to use the ideas that I've described, but to use them in very high dimension and specifically in weather forecasting. And a lot of the systemization of these ideas is due to Andrew Lorentz, who is head of data assimilation at the UK Met Office for many years, recently retired, and two key papers that he wrote that relate to what I'm going to call the 3D VAR method, and I will relate to Kalman filter. This paper in 1986 and a follow-up in 97. The key idea, if you think in terms of optimization, is that what makes the Kalman filter expensive in high dimensions is updating covariances, and the key idea of the 3D VAR filter is to fix the covariances. And simply solve sequential optimization problems, keeping your output or your estimate of the state close to the dynamics implied by the model and the data. And the scenario is sufficiently general to allow a nonlinear dynamics model, whereas the Kalman, just to remind you, the Kalman model had a linear propagator. Okay, so I've now replaced MV, matrix M is replaced by general nonlinear mapping psi. Everything else is exactly the same. And what comes out of this method that I'll describe in the next slide is a mapping from the estimate of the state Vn to Vn plus 1. And the algorithm is very much the same as what I described to you for the Kalman filter. You predict using the model, ignoring the noise. And then you solve an optimization problem which asks you to find your next V to minimize the subjective function, which is the sum of two terms, one of which keeps you close to the prediction of the model and one of which keeps you close to the data. You can solve this in closed form, and because the covariance C hat, which evolved in time in the Kalman filter, is fixed in the 3D VAR filter, this is computationally much cheaper. So you can do all the linear algebra once and for all and use it again and again and again.
Will you be discussing possibly varying the equal weighting of the two?
Yeah, that is in here because these covariances change the weighting. So the point of the covariances is exactly to deal with that issue. The covariances weight these and tell you whether you have more confidence in the model or the data. So that's part of what's in there. Thank you for bringing that out. So in the weather forecasting context, these fixed covariances were chosen to be relatively simple to compute with using spherical harmonics or Fourier structure, and this led to very implementable algorithms that worked even when the state space dimension was high. And for weather forecasting, state space dimension is about 1 billion, so it is high, and carrying covariance matrices that are 1 billion by 1 billion is something you need to do carefully. So this is doable. However, pertinent to the question I just answered, the relative weights that you put on these two terms, the model and the data, really matter and affect how accurate these algorithms are. I'll show you that in a couple of slides with data from the German Weather Forecasting Service. And just fixing this covariance is not perfect from that point of view. And that leads me to the next idea which I'd like to describe, which is the Ensemble Kalman filter. And I'll just say what this is in words and then tell you about who developed it and the history of it. But in words, the idea of the Ensemble Kalman filter is that we don't want to carry covariances of this model because they're too large. We don't want to update them on the whole space for high-dimensional problems such as weather forecasting. And so what we do is we have an ensemble of state estimates, and we estimate this covariance empirically from that ensemble. That's the idea in words. So you have many interacting copies of this minimization principle, and I'll write it down in a second, and they interact through a covariance which is computed empirically from the different ensemble members. Right, and this idea goes back to Geir Evenson, who is a Norwegian, pictured there. Actually, a Canadian meteorologist had more or less the same idea around the same time and published it very soon thereafter. But Evenson has really pushed this methodology very widely, so he's mainly responsible for it. So the same model setup as I had for 3D VAR. So his paper that kicked this subject off is in the Journal of Geophysical Research in '94. This was motivated by something called the extended Kalman filter, which was developed in the electrical engineering literature following on from Kalman. And there's a book by Jarzwinski where you can read about that, which essentially linearizes psi so that you can use Kalman ideas, and was proposed by Michael Gill, who's a meteorologist, in the early 1980s as a method of doing weather forecasting. But these are not really practical for weather forecasting for the same reasons that 3D VAR is not practical. Well, for the same reason that I said about Kalman filter, namely that the covariances are too large. So this idea of approximating the covariances by an ensemble really made things computable, and I'll show you it has a real positive impact. The original paper, and this is a theme I'm now going to take up in terms of the wide-ranging applicability of the idea, the original paper was in ocean dynamics, but rapidly got transferred into weather forecasting. And the very best weather forecasting at the moment is done in the European Centre, which is in the UK. And although they have historically not used Ensemble Kalman filter, they're adopting Ensemble Kalman methods within their methodology, which is termed 4D VAR. And many of the other competitive weather forecasting centres around the world use this idea. So it's been a central idea in combining data and models. So just to flash up what I've said in words, this is exactly the same as for 3D VAR, except that there's lots of notation here, but the n is time as it was before, k is ensemble member, so we have rather than just having one prediction, we have a whole bunch of them, uppercase K, and they all solve a minimization principle, the same as before, but the weighting of the model is weighted by the empirical covariance computed from the ensemble. Okay, so the spread of your possible guesses gives you an idea of the uncertainty in the model, and you use that to weight this model data compromise. And because of the way this is set up, in contrast to the 3D VAR, which needed d squared storage, this only requires kd storage. So d, remember, is 10 to the 9 in weather forecasting. K is typically like 100. So this is a significant advantage in terms of computer resource allocation. It's also inherently parallelizable, so that it maps onto computer architectures that are currently and in the foreseeable future prominent in large-scale computing. So this idea of Evenson has been absolutely central, and I want to just show you a little bit about how it plays out in weather forecasting and explain to you what the basic problem is in weather forecasting. So there's tons of data used in weather forecasting, and this picture is meant to summarize that fact. Satellites, weather balloons, things that are located on the Earth, aircraft, most civil aircraft gather data and share it with meteorological centers. So there's a plethora of data, and in fact a lot of it is not used. There's more data available than is used by weather forecasting centers. The data is large, roughly. You should think of about 1 million data points every 6 hours. But remember, the model is even larger. It has billions of variables. But billions of variables with lots of correlation, and correlation understood through physics. Okay, so there's a lot of data and a lot of heterogeneous different sources of data, and the issue we've been discussing about weighting different things. I talked earlier about weighting the model and the data, but there's also the question about how you weight different sources of data, and is very important and plays a key role in getting improved weather forecasts. So let me just tell you what the problem is with the weather forecasting. It is basically the well-known butterfly effect, that if we don't know, what you see here are traces of a projection onto a particular Fourier mode of the atmospheric dynamics as a function of time, and in blue and in pink are let me get them the right way around. In blue is the true signal, and in pink is a prediction made by the model. And what typically happens in predictions is that because of small errors in how you initialize weather forecasting, the butterfly effect, as named by Lorentz. By the way, I should have said that this Lorentz, is not the Lorentz, but his name is pronounced Lorentz, even though it has a C on the end. So the butterfly effect, the term, was coined by meteorologist at MIT, Lorentz. So this is the butterfly effect, which shows that prediction and model diverge from one another very quickly because of small errors in the initialization. And that's of a particular projection onto a Fourier mode, and this is the overall error grows to order 1 in several hours.
I think one should also mention that because you're comparing with a predicted, therefore computed effect, one of the important factors in the butterfly effect is the precision with which you compute.
Yes, that's true. There are many sources, not just the initialization, but the different precisions will give different. It's in general unstable to small perturbations of all kinds. The next slide shows what you can do with data. So essentially, data overcomes the butterfly effect. So in this toy example, we show how the incorporation of data here with the 3D VAR algorithm causes the predictive signal, which is in pink, to lock on to the true signal, which is in blue, here I'm showing over 12 time units. This shows that the error remains small over 100 time units. And so in simple terms, there are many other issues, but one of the main issues with weather forecasting is the fact that poor initialization can lead to butterfly effect, but data can be used to overcome that, and that's a key part of the methodology that data contributes to making better weather forecasts. And weather forecasts have on average got better by about a day every decade for the last 50 years. And rule of thumb estimates say that about 25% of that can be attributed to data assimilation of the type I'm describing here. So this slide is from the German Weather Forecasting Service, and it shows the impact of mathematics in the form of the Ensemble Kalman filter and how it has improved on the 3D VAR filter. So this graph measures something called skill, which is predictive capability. 1 is perfect, 0 is far from perfect, against time in hours. So just ignore the anomaly correction. So being up here is very high accuracy, and there are two curves here. One is blue, 3D VAR, one is red, the Kalman filter. As you can see, in both cases the accuracy decreases with time, but what you can see is that through using this Ensemble Kalman filter as opposed to the 3D VAR method, the red curve is shifted to the right with respect to the blue curve, which is giving it several hours more predictive capability at the same level of skill. Okay? So this skill is averaged over many different weather scenarios. So these ideas, Ensemble Kalman filter, which built on 3D VAR, which came from Kalman filter, they have a real measurable impact on the quality of weather forecasting. So that alone is a very important success. What I would like to do now is pause and ask if there are any questions. Anyone want to ask any questions?
Just with the Ensemble Kalman filter, because you're adding the noise, then you're assuming knowledge of gamma, right?
Yes. Gamma being the covariance of this noise. That's right.
No, gamma being I thought gamma was the covariance of psi.
That's sigma, I think.
Oh, sorry.
But yes, I'm assuming I know
Knowledge of
both of them,
Yeah.
and that is used in the model.
Is that also a property of the original Kalman filter?
Yes.
You do assume
You
knowledge.
assume that they're known. So everything can be learnt separately from the methodology I'm describing and is in practice. And doing that makes a big difference and is important. So knowing the covariances really has a big impact. And although I presented it as if we know them, in practice we have to learn them, and that's a separate task. It's done in weather forecasting by something called historic reanalysis, which is a historical analysis of past data. Thank you. Any other questions? Yeah.
How do you measure whether the prediction is good?
So this is looking at what computer models predict and comparing them with what actually happened.
What do they predict? It's just not just one variable? Or?
No, so the computer model is something that predicts all of these 10 to the 9 states, which describe the velocity, humidity, or pressure, aspects of the entire physical system at every point on the discretized globe. So it's a very high dimensional vector, but then it's reduced, I don't know exactly how, but it's not a single point, as they would compare global atmospheric conditions through some integrated norm. And so there are universally agreed measures of skill so that different weather forecasting services can make agreed upon comparisons. But the question you ask is a good one, because some people argue that the reason the European Centre for Medium Range Weather Forecasting always comes out best is because they've tuned themselves to the particular metric that appears in all of these graphs, and it's arguably the case that others might be better by some other metric. So you've touched on a big discussion. Any other questions? Okay, so I want to go into a different subject area, which is inverse problems, and then show you how these ostensibly different problems, and the problems I've described are a kind of inverse problem, but I'm going to look at a much more general class of inverse problems and explain to you how Kalman ideas can be used in this context. So inverse problem, don't look for a definition because you'll never find a good one. Joe Keller, who is one of the great applied mathematicians of the last 50 years, has a definition of inverse problem, which you'll find if you look in Google for definition of inverse problem. And it's terrible. I mean, if you read it, it would just put you off the whole subject area. I'll just give it, from the purposes of this talk, we develop mathematical models to make predictions, and those models have inputs to them. The inverse problem is about finding what inputs must have gone into the model to result in a given outcome. And you might be interested in that to learn about parameters in a model, or you might be interested in that to control a system to a given output. So in many cases, you're interested in finding U, so that when you apply G to it, you get a given outcome Y. And often these are underdetermined problems in the sense that the amount of data in Y is a smaller dimension than the dimension of U, in some sense. And there are two, roughly speaking, two camps for approaching this problem. One is through optimization and goes back to ideas of Russian mathematician Tikhonov in 1963. You can read about them in this book here. And then there are more statistical Bayesian approaches to this problem, which view everything as a random variable and try and find the conditional distribution of U given Y. They're summarized nicely in this book of Kaipio and Somersalo. The first mathematical paper to systematize this Bayesian approach to inverse problems was by Joel Franklin in 1970. It's an interesting paper because he formulated the inverse problem for finding the initial condition of the heat equation from its solution at time 1 in a Bayesian way, and it's a beautiful mathematical paper, but it got absolutely no traction because it was computationally unfeasible to do anything with Bayesian methods except on linear Gaussian problems. in 1970. So it wasn't until Monte Carlo Markov chain kicked off several decades later that this methodology became practical for solving large inverse problems. The Kalman methods I'm going to describe are somewhere between these two, and I want to show you a little bit about how they work mathematically and the applications to which they apply. But the basic take-home message is that these methods have, I think, a lot of potential to be applied in many different areas. So the idea, let me just remind you, I'm interested in solving the equation for u, y is g of u plus eta. I'll write it on the other side. And the idea that I'm writing on this slide is there's no dynamics in this equation. But the idea is to introduce an artificial dynamics. So the dynamics is trivial. The thing you want to estimate doesn't change. And the thing you observe, that's y, is going to be is just g of u. And so you then hypothesize that the data is w, which is g of u, plus noise. And then you just iterate that. So this is really writing down this equation multiple times. Okay, so how do you use this? Well, you have to create data. We only have one data point here, whereas here we have several data points. And there are lots of issues about how you scale the covariance to compensate for the fact that you're reusing the data again and again. I won't get into them in detail, but those are issues that are addressed in this field. And I will formulate on the next slide this problem in the notation that's in the two boxes. But just let me give you a bit of history of where this came from. So Evenson was Norwegian. He introduced the Ensemble Kalman filter that I told you about earlier. His original paper was in oceanography. That was his initial field. Norway, as you all know, has a large investment in oil industry, and Evenson moved to Statoil, which is the Norwegian primary Norwegian oil provider, and that precipitated a development of the use of the Ensemble Kalman filter away, or in addition to weather forecasting, and into the oil industry. And it's also used in related problems such as hydrology. And there are a number of people who've contributed, including Evenson, to that transfer of technology into this oil industry. One of them is Geir Navdal, also Norwegian, wrote a couple of key papers in the early 2000s. And others are Dean Oliver and Al Reynolds, who wrote a nice book on the use of Monte Carlo methods, and in particular Ensemble Kalman methods in the oil industry. And that's Dean Oliver there. Al Reynolds is the author of a famous numerical analysis textbook, Burden, Fairs and Reynolds, if any of you know that. Okay, so a bit more mathematics, but firstly, the equations that are, this dynamical model can be cast in the form of the equation in the box by letting Vn be Un and Wn, and letting H be, H being the observation operator, being just projection onto the W coordinate. So the take-home message of this box here is that when I wrote down the iterative in time version of this inverse problem, it can be cast in the form of the problems I solved in the previous section through Kalman filter, 3D VAR, and Ensemble Kalman filter. The content of this slide is just to show you and give you some idea about how what does the Ensemble Kalman filter actually end up doing. So if we apply the Ensemble Kalman filter to this inverse problem setup, and you take a continuous time limit, you get a system of ordinary differential equations for the ensemble members. So dot here is differentiation in time. Time is algorithmic time that was introduced artificially to solve this problem. So you have a bunch of particles that try and estimate u to satisfy the equation y equals g of u, and there are uppercase k of them, and they interact according to this flow here. And DKL, I think the thing to take away from this is that this interacting particle system induces two things, one of which is that it drives the solution towards the data, and the other thing is that it drives the solutions towards the particle system towards consensus. So it likes it if the particles agree with one another, and it likes it if the particles agree with the data. G bar here is the average of the G's over all the different ensemble members. So you won't take that in unless you've seen something like it before, but those concepts you can take away from this. By the way, this is joint work with Claudia Schillings, who is somewhere here, the very back corner. The methodology drives towards the data and drives towards consensus. And using that, you can show that what it does on linear inverse problems is perform a gradient descent. Each particle performs a gradient descent, but it's projected into the span of all the other particles. So the consequence of that is that the ensemble algorithm minimizes the least squares objective function over a finite dimensional subspace, which you can characterize in terms of the initial span of your particles. So this is as mathematical as I'm going to get, but I wanted you to know that the ensemble Kalman filter is incredibly widely used and very little analyzed. This is about all we know about it. There are a few other things, but not much is known about it. So it's an opportunity for mathematicians because it is widely used, very successful, and yet hardly understood from a rigorous point of view. So I want to spend the last few minutes showing you some applications of the ensemble Kalman filter to inverse problems. I'll write them in math and in pictures. So the first problem is groundwater flow. So let me just describe this in words. In words, this is a problem of interest to hydrologists who measure the height of the water table by putting things into the ground. The height of the water table, that's the height to which the water rises inside the porous medium which constitutes the subsurface, is a surrogate for the pressure in the subsurface. And the pressure solves a partial differential equation which takes as P as the pressure, which takes as coefficient kappa, which encodes the material properties of the subsurface. What that means in words is that if you measure the height of the water table and if you solve an inverse problem, you can learn about the material properties of what's underground. Okay? So that's obviously interesting to many people, hydrologists and people in the oil industry. And there are generalizations of this which are used for the modeling of two-phase flow, which is oil and water, three-phase flow if you have gas in the oil industry. So the inverse problem in math terms is to learn about the coefficient of this partial differential equation from measurements of the solution, which is the pressure. So let me just show you, to give you an idea of where ensemble Kalman filter goes, a specific geometric example. So in the subsurface, one thing that's of interest are formations of different kinds of media that come up against one another. So for example, historical riverbeds leave sandy deposits, which is here represented by this channel, which may be surrounded by harder material that's less porous.
Or softer material.
Or softer, depends.
You see that in the fenlands around here, that you can see the old rivers running like ridges across the fields because they're firmer, being sandy. And so when the fens dried out, the other stuff sank, and you can see the old riverbed raised above the...
Yeah. Thank you.
And that has an implication for water flow.
It does, and so that's exactly why people are interested in this problem, is to find channels in which water will flow easily or less easily.
Well, you can't flow along the channel because the channel is raised.
Yes.
And it has to rise to a certain height before it can flow across the channel, because the channel is less pervious. It's like a bank.
But in the subsurface, the sandy material is the more porous medium. And the medium that's surrounding it is the less porous and the less permeable medium
typically.
afterwards, once it's underground.
Okay, so what I'm going to show you is how the Ensemble Kalman filter recovers something of this type. And in a sense, I'm showing you about parameterization. So we parameterize this geometry through 5 scalars, and then we have random fields that describe the interior and exterior of that geometry. And this just shows you something about how the algorithm works. We learn the geometry as the algorithm progresses. This is subsequent steps of the algorithm. We learn the geometry, but we also learn about the contrast in the medium. What you see from this, if you compare the output of the algorithm with the truth, which is the true, this is a simulation study where we have access to the truth, we recover, this implies that the data contains a lot of information about the geometry, but if you look at the details of the field inside and outside, that is not, of course, very accurate. Okay, so that's one kind of problem in hydrology. Here's another problem in medical imaging. You won't take these equations in unless you already know them, so I won't even try to describe them to you. They're similar in form to the previous equation, but in detail more complicated. But electrical impedance tomography is a potential method of medical imaging. It also goes by the name ERT, electrical resistance tomography, and is widely used in subsurface imaging in addition to the methodology I just described. And the method here is to inject current on the boundary of a domain and measure the resulting voltage. So here you inject current at these blue points here, and you measure the resulting voltage, and that gives information about the resistivity of the interior medium, and in case of medical imaging can be used to diagnose healthy and unhealthy tissue. So you should think of unhealthy, healthy. So this is an example where we try and learn these inclusions from the measurement setup I just described, and here we use what's called the level set approach, and I'll just explain that to you on the next couple of slides by means of pictures. But as well as the level set function, which I explained to you, we also have to learn some length scales and smoothness properties of that function as part of the algorithm progresses, and we do that. So the idea of the level set method is, although we're trying to reconstruct something which is piecewise constant, we work with a continuous function, which you see here, which is thresholded to give the function we're interested in. So this is the space where the algorithm works, and if you take the sign of this thing and color it red where it's positive and blue where it's negative, you get this, and this is well matched to the true inclusion structure that we had at the beginning. So the takeaway of these 2 examples is that there are many interesting examples that can be tackled by this methodology, 1, and 2, that how you parameterize the models can have a big effect on how well they work. All right, I'll spend the last 2 minutes just tell you about a problem in machine learning. So this is a well-trodden data set that was introduced as a testbed for what is called supervised learning, and which I'll describe in a moment, by Yann LeCun in 1999. He's a professor of computer science at NYU and also works at Facebook Research, and has been a leading proponent of bringing neural networks, which were developed to a very great extent in the 1980s, but then went out of fashion, bringing them back into use through clever design, use of advances in computers, and good choice of applications. So the objective of this problem is to be able to recognize digits automatically, and just flash up how these methods work. They're trained with data where you give the algorithm digits and you label them. So the input here is a digit is going to be a pixelized image with a gray scale. So it's a bunch of real numbers, thousands of them. That's the input, X, and you label them, or someone labels them, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you train a function which agrees with the data you're given, which is a mapping from the grayscale pixelated images to 10 outcomes, and you train parameters U that try and make that a good fit. And then the idea is that you use that to predict when you use it, when you apply the function to points x that are not in this data set. That's supervised learning, and I could say more about it mathematically, but let me just show you the key take-home message, which is included in this slide. So this can be formulated as an inverse problem and can be solved by the Ensemble Kalman filter. What I'm showing you here is a measure of the accuracy. So how accuracy is tested by this data set, the MNIST data set, contains 70,000 digits. 60,000 of them are used to train the algorithm. That means learn the parameters U, so that the mapping, which is in this case a convolutional neural network with 2 layers, so that the mapping from the input grayscale image to the classification as a digit fits the data, the 60,000 data points that you know, and then is tested against the remaining 10,000 in terms of accuracy of prediction. The state of the art for these algorithms are based on what's called stochastic gradient descent algorithms for fitting, and the ADAM methodology takes that and adds to it ideas due to Nesterov in convex optimization, which add momentum to gradient descent. So ADAM is really the state of the art, and what you see here, ADAM is in blue, a good implementation of stochastic gradient descent in yellow, and Ensemble Kalman filter in orange. What I'd like you to appreciate is that all of them are extremely accurate, and in particular the Ensemble Kalman filter is as accurate as the other two, although it takes a little bit longer to get there. This is interesting because there are many tens of thousands of people who have worked on optimizing these algorithms, ADAM and SGD, for tasks of this type over the last 10 years. Literally tens of thousands of people. And it's very impressive that the Ensemble Kalman filter can come into this domain and produce comparable results on a very short time scale with very little tuning, although we have used many of the ideas that go into the details of how ADAM and SGD are implemented. But I wanted to show you that because I want to conclude by pointing out that not only did Kalman's paper make an immediate impact in the decade it came out in terms of aerospace guidance and landing on the moon, revolutionized applied mathematics and the way we think about data and interface with model, but the range of applications is enormous. I showed you that the Ensemble Kalman filter started in oceanography, went into weather forecasting. I'm actively engaged in a model, an attempt to use it in climate models to learn parameters. I showed you applications in geophysical and medical imaging, and at the end in machine learning. So this is a methodology which I think has a lot of potential application. It's very straightforward, black box in terms of being able to use it, and so proving to be tried and tested, and yet very little mathematics about it. So there are opportunities for mathematicians to systematize the field. So I hope I've shown you something about what Kalman did for us all in 1960, and thank you for your attention.
Okay, we have time for questions. Right.
Extremely naive question, Andrew, sorry. All of this stuff seems to be discrete, but then you developed a continuum version of it. Now, if ever you wanted to implement that, I presume you'd go back and discretize it.
Yes, you would.
So, what were you gaining?
Insight. So, firstly, Kalman published a paper in 1960 at the same time, which was in continuous time, just more complicated because it involves stochastic differential equations, so I didn't write it down. If you have high frequency data, those models are probably the right way to think about what happens when you have noise, which is very high frequency but independent at each time. So that's the justification for Kalman's contribution in continuous time in the 1960s. The continuous time limit I wrote down, I do so for insight because I can understand a lot more easily what that flow does than I can if you give me discrete time. And also, if you look at many machine learning tasks, they are also formulated as discrete algorithms. And if you like, what you're trying to do in that MNIST dataset problem, what the neural nets do is they change coordinates to kind of separate the data so that the 1s are over here and the 2 is here and the 3 is here. If you start to think about that in terms of flowing rather than the discrete thing which takes you from one place to another, I think you have more intuition about how you might go about doing it, even if eventually you discretize to implement the algorithm. Because continuity, I'm sure you wouldn't disagree, continuity buys you a lot in terms of insight. So that would be my argument.
So the cost of the ensemble common filter is OKD rather than OD
For
squared.
storage, yeah. Because you basically you have k vectors of length d.
Right.
And then you just do operations on take inner products with them.
Right. But obviously you're committing some sort of error.
Yes.
Does that lead to a bias in the results?
Yeah.
And is that well understood?
That's a good question. Yes, it is quite well understood. So I said with respect to inverse problems, there was an optimization perspective and a Bayesian perspective. Although Evenson, if you look at his papers, he tries to derive the Ensemble Kalman filter from the point of view of a Bayesian perspective. It's not consistent as you take n to infinity, k to infinity, where k is the number of particles, except in the linear Gaussian, the case, Kalman's case. In Kalman's case, it is consistent as k goes to infinity. In the nonlinear case, it's not consistent with the true Bayesian posterior distribution. Its limit is another measure, which was characterized in a paper of Oliver Ernst and others. So it's understood not to be consistent. So on the other hand, the perspective I gave was just to view it as an optimization algorithm and ask how good it is at minimizing a least squares loss function. And in that sense, it's provably good on the linear problem, but we don't have any proofs, just empirical evidence as to how it behaves on the nonlinear problem. And the final thing to say in response to this, which is a really good question, is that the reason people like the Ensemble Kalman filter is because they can use it practically and get meaningful state estimation with a small number of particles. So they don't take the large particle limit. So the particle filter has been very successful and is developed because it has a nice theory when you take the number of particles to infinity. But in reality, if you're running a model of the climate or weather, you've just got 10 or 100 copies of the model. And the more relevant question is not what is the asymptotics as I take 1 billion particles, because you never will. It's if I run 10 or 100 copies of the weather, what's the best thing I can do with them and how should I interact them?
Yeah, that's what I meant by
when
I was asking. Is it understood? So are there error bounds on?
No, so there aren't, and it would be there are there's a limited amount on optimization, but there's very little on how you might place them to optimally represent the probability distribution given 100 points. I think that's a good direction for research because there's nothing done on it, and we've been having discussion, some of us, about that.
Okay, there should be some wine and hopefully other drinks outside as well, so we can continue discussions more informally. So please let's thank Andrew again.
Thank you.